Yes.
Okay. Yes, I'm sharing my screen. Let's see. This is what I want to share. Okay. So do you see my PPT presentation?
Yes.
Okay. So microcore applications. In retrospect, I would say I should have done this as a first presentation, because this, I think, gives a lot of motivation and also gives you a better idea of what microcore can be used for, because after all, it is a very high performance Forth engine. Anyway, so let's start. This is the list of major applications I have been doing over a period of altogether, well, let's say 15 years or so. And I go through them project by project. The green numbers to the right are the types of FPGAs I'm using. And since this is all a while ago, these are all 90 nanometer technologies, which means they are quite old. But anyways, they are big enough for microcore and additional stuff that is needed by the application. Geo Geon MCS. This is an offshore seismic data logger, and offshore means besides the XYZ axis of geophones, we also have the hydrophone pressure, the so-called Z component. So this is actually a 4-channel data logger. And this is also the reason why commercial land seismic recorders cannot be used for this purpose. And this is, well, it's not very complicated. We have 24-bit digitizers, and we have a very, very high precision time base that is not allowed to consume any power. This is a contradiction, but there is, in the US, there is a French guy who specialized on these kinds of time bases, and he gets a precision without heating and with a crystal oscillator of 1.5 seconds per year, which is excellent and good enough for the seismic data loggers. And the time base is important because several data loggers are deployed on the ocean bottom for one experiment, and later on, when you correlate the signals, you are dependent on the precise timing to get the correlation right. The digitizer fills a 4 megabyte buffer, and whenever the buffer is almost full, it is written out to a disk, and the disk can be read. At the time when I did this, it was not clear that how do you call the technology of Microsoft? Anyway, it was not clear which was the quickest, and at the time, the 400 megabit per second FireWire was the proper choice. And nobody would know that this is going to die. So this is a block diagram, and this is how it looks like. There is the Xilinx FPGA in the very center. You don't see it in the picture. And it runs microcore. And one of the nice things is the type of data compression I'm doing. It's here you see the actual high-level code of encoding a single sample. Oops, what happened? To encoding a single sample. And if the thing runs at, well, let's say 1 kilosample per second times 4 channels, this is clear that this is a bottleneck. And by realizing these 1, 2, 3, 4, 5 instructions, functions as microcore instructions, the whole encode game can be reduced to this expression, which is dramatically more quicker. So with this, we were able to do the 1 kilosamples per second sampling rates. The next project is the ultra-wide dynamic range ADC. It has 150 dB dynamic range, which usually you would say this is not possible, but the way we did this is the hydrophones and the geophones, they always feed 2 channels. Then the amplification of these channels are different, and I skip ahead and show you. Now, this is what the 2 different ADCs do. There is one that is an 18-bit A to D, which is very sensitive. And then later on, there is also in parallel a 16-bit ADC that has a much lower sensitivity. And here you see the combined action of the so-called fine ADC and the coarse ADC. And as a matter of fact, when the seismic signals are evaluated, what is really important are the faint signals. So usually we are only in this region, and sometimes the boat that makes the noises passes a seismic station, in which case we get into this region, but then the resolution is not that important. So this is the block diagram. We have 2 channels for the hydrophone, 2 channels for the geophone. And then we have, again, a Xilinx XC2V250 that combines all these channels, and especially the most computing power of the FPGA is taken by finite impulse response filters that produce the different sampling rates, because these ADCs work at standard speeds and always the same. And so the reduction of the sampling rates is being done by low pass decimation filtering. And here you see a real, I mean, this is real data that has been taken, and you see, yes, we were able to make in the fine channel, we were able to do the 150 dB dynamic range. And here you see the noise signals, the 50 hertz, and the third overtone of the 50 hertz as noise signals, which if you work in a urban environment, there is no way around these noises, but of course, on the ocean bottom, they are not present. So that was an enhancement of the Geo Geon MCS with an extended dynamic range. The next project is Sugar. Sugar is an acronym, and I don't remember what it stands for, but in any event, this was a large project that kept us busy for more than a year. There is a boat, and the boat has a coaxial tow cable, which in this case was 7 kilometers long. And then comes they call it a pick here in this picture. So this is a larger structure, which you don't see here either. Oh no, this is the heart of it. This is a titanium pressure housing with all kinds of electronics in it. So this is in this part. And then comes the streamer, which is a chain of hydrophone, pressure, and compass information. With the pressure, you determine how deep the hydrophone housing is immersed in the water, and it is precise enough to detect differences of more than 1 meter. So you can see whether this is a straight line or if there are wiggles in it, and that is all important when you evaluate the seismic signals. The compass is needed in order to see whether if you look from above, whether it goes in a straight line or has, if the the ship makes a turn, then this is, of course, no longer a straight line. So you see this from the compass. And the hydrophone actually is responsible for the types of signals that are supposed to be picked up. And yeah, this is a large setup. And here you see some components. These are the streamer nodes. Here you see an opening, and behind the opening is a hydrophone, and they are all interconnected. And the data is collected. There's always, I believe it was a 10 megabit per second frame that traveled from the last node towards the receiving station here. And the receiving was done by this PC board with an FPGA on it and microcore. And basically what it did, it converted the serial stream that came in, converted it into 24-bit entities for the hydrophones, and then it would send these, the FPGA and microcore would send these signals to a bottom PC, which was quick enough for this purpose. And this one did two things. It stored all the data that was collected on a fixed disk, and a selection of up to, I believe it was 10 hydrophone nodes or so, immediately shipped it to the boat for inspection by the crew that was observing it. And here, for instance, you see the modem that would receive the TCP/IP signal from the PC here and send it and this unit here couples these signals into the tow cable, and that bridges the 7 kilometers to the boat. And here in this example, we used a lattice FPGA, the XP2-17, which turned out to be large enough. The next project is the Korean ocean bottom system. Since we had the know-how how to operate on the ocean floor, it was more or less easy for us to get a foot in the tsunami warning market after the big tsunami in Indonesia, when all of the large companies in the world didn't have anything to offer, and we could quickly come up with a solution. And so this was built on an island in the Japanese Sea off the coast, I think about 80 kilometers off the coast of South Korea. There was a meteorological station on the island, and that kept all the equipment on land that was necessary to operate the system. Then there was a land cable to a beach hole, and in the beach hole, the land cable was coupled to the underwater cable to connect to the ocean bottom unit, as we called it, that had the electronics and the sensors. Well, the major sensor of this installation is a pressure sensor of Pyroscientific in, I think they are located in Seattle, as far as I remember, and it has an unbelievable precision. So in a water depth of 3,000 meters, you could detect changes in the water level of 5 millimeters. And this turned out to be sufficient to find tsunami events. As a matter of fact, in the area that the system was operating, the tides wave was about 40 centimeters. And on these 40 centimeters, an irregularity of 2 or 3 centimeters constituted a tsunami event, and that of course needed to be detected with appropriate algorithms, and these algorithms were here running on the LAMP station. Laying the sea cable was quite an experience, so this was an opportunity in my life to work on a cable laying ship, and that was very interesting. Here are some components. This is the ocean bottom unit photographed on the seafloor. This is the ocean bottom unit on board before deployment. And the thing about optical cables is, in an optical cable, you have fibers and only one conductor, because the fibers are contained. In our case, we used a very advanced optical fiber that kept the optical fibers in a copper tube. And so the copper tube was the actual electrical conductor, but there was only one. So the current that had to go back to the beach, well, that had to go through the water. And so here you see the combined system and the electrical situation. We built a constant current source of 460 milliamps. And then already the land cable was 63 ohms, 5 kilometers. And then the 20-kilometer sea cable was another 31 ohms. So these all incurred losses on the way to the OBU. So here we lost 29 volts, here we lost 14, and the OBU itself consumed 12.7 volts. And then the return was from an electron trode on the OBU, which is the cathode, because the anode more or less disintegrates, and we didn't want anything to disintegrate deep down in the sea. By the way, deep down means 2,200 meters in this case. And so the current travels through the water to a beach electrode. And interestingly enough, the sea bridge, so to speak, it kind of was very similar to a Zener diode, because once you are further away than, I believe, 5 kilometers or so, the voltage drop would always be 5.2 volt. Why? Yeah, because the only narrow spaces was the electrode on this side and the electrode on this side. These were more or less small, but then the ocean can be thought of as a conductor of infinite widths. So the water itself doesn't produce much of resistance, but the resistance is concentrated around this electrode and this electrode. So that was COPS, and again, we did it with the lattice XP2-17. The next project was also something unique, a 250 amp and 100 volt current source for a proton cyclotron bumper magnets at a specified precision of 10 ppm, which is quite a challenge. And especially since the 10 ppm precision had to be maintained down to a static DC level. And this is something that will be destroyed by the temperature coefficients of the involved operational amplifiers. So what we did is we put two copper layers on the printed circuit board, both 100 micrometer thick. And these copper layers would then be heated up to 52 degrees. So after 2 hours or so, the entire board would be heated to a stable temperature. And this way, we also got the 10 ppm precision at static DC levels. What is a bumper magnet, or what are bumper magnets? Well, if you have a proton cyclotron, during the running of the protons around in circles, more and more protons would catch up electrons and kind of disappear from the stream. And so every now and then how do you call this? The plasma that runs around was diverted and sent through a chamber that would again, I don't remember how, but that would again produce enough protons for the next, let's say, period of the cyclotron running. And here you see then very quickly the proton stream would be switched or diverted to this proton enhancement chamber, and then the protons would be generated, and then you would slowly switch it back to the cyclotron for experiments. So that was a CCD1. And then the last project that I did before retirement was the Merlin Satellite's frequency reference unit. Merlin is a satellite that hopefully will be deployed in 2027 or so. And it is supposed to measure the methane concentration in the atmosphere at a precision of 150 by 150 meter rectangles, so to speak. The way it is done is quite simple. Methane has a very, very specific absorption spectrum. You see this dip here. And this absorption consists of 6 spectral lines that are kind of very close to each other, so they add up to this response. And this is unique for methane. There is no other gas in the vicinity that has a similar absorption spectrum. So what is being done is one laser pulse is sent, you see this yellow line here, is sent into this absorption region. And then the backscattering is picked up by the satellite and its magnitude is recorded. And 200 microseconds later, another laser beam is directed towards the Earth. That is 10 gigahertz away from the first pulse. And so in the backscatter there, you receive the energy when there is no methane backscatter. And so from the difference of the backscatter signals of these two signals, you can easily determine the methane content. The difficult part of this is to generate the needed laser frequencies that and these are generated by solid state 10 milliwatt laser diodes, and that is what the frequency reference unit and microcore in this case did. It stabilized the laser frequencies to produce the laser diodes to produce these two frequencies, and these 10 milliwatt signals were then be used by a high energy laser system that is pumped and where the laser signals runs in circle until one of the mirrors is switched off and the laser beam is released from running around. Microcore in this case was only used, or is being used in this case, in the engineering and qualification model, because unfortunately Microcore is not a certified processor as far as the as satellites is concerned, and therefore it was felt that it would be much easier to re-engineer the whole thing and do all the control in pure VHDL without processor, and that this would be cheaper than certifying Microcore itself. In retrospect, it turns out that it may have been cheaper to certify Microcore, but this is not how the project went, unfortunately. And some more words about, well, how is the synchronization done? There is a so-called absolute frequency reference on board the satellite, or as part of the frequency reference unit, which is a tube filled with methane. And then a laser beam is sent through this tube every now and then with laser diodes, with receiving photodiodes before the tube and after the tube. And so the absorption of the tube can be measured. And so in that respect, it is very easy to find exactly this region on this frequency. And then there is a very simple wave meter also on board the satellite, which consists in its very heart of a 760 pixel sensor line and a so-called FISO is used to scan the laser signal or through the scan line depending on the frequency. And so we have the absolute frequency with a wave meter, we have a relative deviation, and so we can precisely determine this point as well as this point. Okay. So these were the major applications. Besides these, there were quite a number of ad hoc projects that we did in order to build measurement instruments and whatnot that were needed to realize the projects during the engineering phase. Okay. New developments in Microcore. I tried to realize UDP-TP on Microcore. I did not even try. I realized it actually without byte addressing, and it turns out that this can be done quite well and is quite efficient, but unfortunately, all the existing large IP packages depend on byte addressing, and so with my approach, I couldn't use any of those. And so I came to the conclusion bytes are actually needed sometimes. And so I took the time and built byte addressing into Microcore. And now you have all possibilities, because byte addressing only makes sense if you have a 16-bit or a 32-bit or a 64-bit architecture. because with other word widths, the concept of bytes doesn't make sense because you cannot really address it in a linear address range. And so you have now all words available. You can do everything as before. Microcore is a cell-addressed machine with arbitrary word widths. And if you have 16 or 32 bits, you have a choice whether you want to use cell addressing or byte addressing. And while I was doing this, it became clear to me that the test of the division instructions that I had done long ago had never been completely tested, but I had stochastic tests, and the stochastic tests looked nice. But what if I did a comprehensive test? And it was possible to squeeze the software that is needed for an interactive test of dividing a number by a divisor and then multiplying the quotient with the divisor and adding the remainder, and then you should get your original dividend if everything is fine. That the code to do that and also with an interactive terminal present as a second task does fit into 1022 instructions. And that means 1022 instructions can be addressed by a 10-bit architecture. And so I did a 10-bit microcore running this program. And then it turns out that the time needed for a comprehensive test of division and multiplication, that means 20-bit dividend divided by 10-bit divisor, takes only 4 hours. And so after 4 hours, all the number combinations have been tested. And as it turned out, the math itself was correct, but the overflow bit had quite a number of errors. And sometimes a wrong result would be computed because of overflows, but the overflow bit was not set. And that has changed now. And now microcore also has a proven precise division and multiplication. Okay, that's it for today.
Great, thank you very much. So I think that was a very great overview of the applications that you did with